Welcome to this webinar. Um, just a note, please type your questions in the Q&A tool. We prefer that instead of using the chat tool for typing those in. That's me over there at the right. My name's Kevin Core. I included this because of bicycle commuting year round, and a bike frame is what Yogesh and I are about to use illustrating our message. I'm based in Northern California, and I've had about the last 2 years working with Yogesh and Dassault Systems partners on our shared mission to help you harmonize product, nature, and life by providing virtual universes to imagine sustainable innovations. So one way to express imagining that universe is to show our software's roles, correlating people and Simolia's capabilities. One focus of today's webinar is revealing how those of us near the origin of this graph access the vertical axis extreme, specifically durability, and also the multidisciplinary optimization engineer role. So durability simulation is contained in a role that is among the strongest structural simulation capabilities. If you're familiar with SOLIDWORKS Simulation Premium, then this role is at the premium end of Simolia's portfolio, analogous to that, with a more robust set of tools, elements, kinds of simulation, and computation alternatives. I see where it says there SPH and CEL, which stand for smoothed particle hydrodynamics and coupled Eulerian Lagrangian analysis for fluid structure interaction. Those are two of the many other powerful tools that require, for instance, no fluid mechanics, COSIM, in order to operate. They are completely self-contained within our structures end of the portfolio. Have an acknowledgement. Thanks, Shreyas, for the physics simulation. Here's the plan. Remainder of my end of things today will be devoted to showing that if you know some SOLIDWORKS, you already kind of know what you're doing in terms of doing this kind of workflow. If you already know it, you'll be able to get this model ready for analysis and also for casual users' use as well. So you designer level users. And at the turn there, I'll invite Yogesh to the stage where democratizing and optimizing against KPIs will come easily. And we'll hang around afterwards for questions. So to begin with, I'll just go into SOLIDWORKS a little bit. Here I'm using the rollback bar on a SOLIDWORKS model to show the history-based parametric solid modeling. One thing in particular to democratization is preparing your SOLIDWORKS model for robustness over the range of values available to users. One thing I just see here that I'm clicking on this thicken feature just to show that I'm creating the gusset from the tube surface there. Just rolling it forward. So I've also got, a layout sketch here that kind of is a sort of the skeleton of the rest of the model. And I've used this in my model to basically make it easy to find everything so that everything I want to change is in one place. And that way, when I want to test for robustness, testing the parameters, testing the dimensions values through their extrema, so that my geometry always rebuilds, is a big takeaway from this. And you can avail yourself of the parametric solid modeling strength of SOLIDWORKS to accomplish that robustness. I will suggest one possibility is to use a design table to quickly identify the coordinates of values that cause the geometry to fail at first, and then from there resolve so the model behaves as predicted over the range of the parametric values. And then from the equations object of the tree, I've gotten into the parameters dialog to basically add parameters and associate those parameters to the dimensions so that when you make a change to a parameter's value, the dimension changes and the dimension drives the geometry change. And just to note, the integration to the platform is within SOLIDWORKS. So it's very easy. No, you don't have to worry about creating step files or things like that. And you'll get the geometry into the platform, and a change made in SOLIDWORKS can be cascaded very rapidly into the platform. So changes are totally associative. And not only are they associative, but they're also bidirectional, so that using this parametric bridge, I can create a little knowledgeware object, as it's called, on the platform, to basically keep the parameters in the specification tree over at the left. So as I finish correcting my spelling there's my object over in the left, upper left. You can see there as I expand the relations in the parametric list there. And I can come in and just maybe add a range to the parameters so that the user knows what the range is and they can easily stay within that range. So parameters varied by a casual user are easily done in the 3DEXPERIENCE tree. So next, I'll use the power of our automation capability to automate creating the meshes, assigning material properties, and doing the mid-surfacing on which we'll create those meshes. And then we'll put some connectors across those meshes so that you have a weld established. So here I'm just automating the process of meshing everything by specifying the various parameters. Going to use a surface quad element topology. And there's my mesh. So automatically create mid-surfaces and meshes for quick simulation model builds. Also, mind you that you can basically replicate your meshing wisdom off to your colleagues by accessing your presets, allowing them to access your presets, which is a huge multiplier in time savings for them. And here I'm using our other detection tool, which allows us to automate the possibilities of creating a connector between the tube and the gusset. And you'll see that it can do many at once. It's very powerful because it not only allows you to create a weld mesh, but also create the transition zone between the tube and the weld, and then the weld and the gusset, so that it automatically creates a transition zone or a mesh gradient, so that optionally you can have a nice gradient into that weld zone. So speaking of welds, I thought I'd go into a little bit of detail, not too much, but maybe a minute or so of what is the importance of durability simulation. To understand the importance of durability simulation, I thought maybe we'd take a minute to consider an example published by a car maker at the Simulia user conference. Here we're looking at a car suspension knuckle. Let's compare the failure locations um, uh, uh, physical test against simulation results. So in this particular case, the car maker had a low-level loading, presumably to represent the normal expected loads in the road exciting the structure. So in the physical test, the knuckle breaks near the mounting holes. And in the analysis, that same location is predicted. So this would be the location of highest stress. As a fully reversed loading, this could be predicted just from the strength analysis or the FEA. Then an overload case, presumably to represent an extreme event such as the curb strike is tested. Repeating this, they get the failure near the mounting bolts in the test, which again is predicted from the analysis. But then they do a single overload before repeating the low-level fatigue again. At that stage, with everything we know so far, where would we predict the failure? At the mounting location. It's the highest stress location. It has the lowest life in each individual case. So combined, this must be the worst location. However, the car maker knew from their tests that this loading caused failure in the arm away from the mounting locations, a result which cannot be predicted from just the base FEA strength analysis load cases and just combining the damage. So fatigue analysis with our solver, which is the FE-safe solver underneath in the technology behind the 3DEXPERIENCE platform, could predict this failure location due to the overload residual compressive stress, which arrests the damage near the mounting, and the overload residual tensile stress in the arm, accelerating the damage there. This is an effect that only appears when you sequence the loads. So in conclusion, performing a durability simulation helps gain accurate insight on regions of failure and hence predict product life. This information can't be obtained with stress analysis alone in cases where the product or structures are experiencing multiple load cycles, during operations in the field, which is pretty common. So I'll sequence the loads in the writer's effort. I've made an analysis case consisting of the two steps already. So we've already done one. I've already done a structural analysis with the results, and I've got results already to go. And I've basically created this case consisting of two steps, one for the left foot and one for the right foot. And I'll sequence the results for the durability analysis case, bearing in mind the importance of sequencing that we talked about just before. So things like surface finish and the sequences to be superimposed is input in the fatigue event. And by the way, if you have transducer data from measurements using accelerometers and strain gauges, you can import those and they can become references in traceability. So I'll use base metal fatigue as a guide for identifying areas of interest for downstream weld fatigue. And here's our results for the base metal fatigue. And this basically allows you to see at a glance what the expected life is sort of a without using the welds um, as a topology. But first, let's just explore why do weld fatigue? Well, the reason to do weld fatigue is that um, the base metal fatigue isn't so conservative as it should be for welds. Welds have a very specific geometry, and so you can get a lot lower fatigue life. Um, so that's why you'd use some sort of code that embraces weld fatigue. The vast majority of people out there are doing only toe failure analysis driven design. With our roles, you cover all modes of failure. Um, we assume as welded or without treatments in the fatigue curves. So you might do shot painting or some thing like that. And if you do, some of our customers do as well, and they develop their own SN curves for their own processes of welding. So if they are routinely grinding the toes, they have a proprietary standards that can be used. But out of the box, the assumption is that residual stresses are pretty near the yield stresses. And that means SN curves have near yield built in. Um, Along that line, there are options in our curves that are available to you for Battelle compressive. So there are definitely, so if you want to model right now out of the box, you've got the capability to do you know, weld fatigue comparison against less conservative fatigue curves. And this just illustrates all the types of failure that you can simulate. And what we'll do here is it basically just picks the lowest life from the analysis and the boundary conditions and the combination of material distribution and load distribution to find what the lowest mean fatigue life is for any of these 8 toe failures or fusion or root, for instance. And so with Verity, the value of the post-weld treatments can be simulated. Think of comparison of the results, SN curves from Battelle residual compressive stress testing, or get a sustained contrast between life of stitch and all the way around welds, for instance. We enable you to design with a basis in simulation of the typical failure modes before committing to welding. I'll go ahead and collect the welds here in the weld fatigue dialog box. So all the welds, all those line fasteners that I created, that's what they're called, the weld connectors. And this is also where you can opt to choose from among the ASME or BS7604 or Battelle compressive loading to compare against the combined loading and material distribution that produces the mean fatigue life. And this is all courtesy of our Verity weld fatigue simulation tool. And you can compare here the log of life considering the Verity and also the contrast between that and side-by-side comparison with base metal fatigue. This all happens very quickly, especially with this kind of a mesh. It's very suitable for democratization and optimization types of analysis. Well, this scenario for fatigue simulation is probably somewhat advanced for a casual user to just get done right the first time. Yogesh is eager to show how to put your choice of tuners and sliders and adjustments to parameters in front of a casual user that makes them independent, even with this maybe more a little advanced analysis. So at this point, Yogesh, welcome to the stage.
All right. Thanks for the introduction, Kevin. Let me share my screen.
Sure.
Okay. Do you see the slide in presentation mode?
Yes, I do.
All right. Thank you. Okay. Hello, everyone. My name is Yogesh Parkhi. I'm a senior industry process consultant at the Source Systems based out of Toronto office. I'm a part of Partner Excellence team where I work with different partners and help them resolve their customers' technical issues. And I also do enablement around simulation. Now, coming back to our bike frame simulation, I mean, imagine a designer or a non-expert simulation engineer trying to build the simulation workflow that Kevin just showcased. Let's say if they are not familiar with the process, it can be quite challenging because they would have to extract the mid surface to reduce the mesh count for meshing purpose, define the appropriate mesh size, set up the weld connections, define strength and durability scenarios, and make sure that boundary conditions or fatigue parameters are correct. Because any mistake can drastically change the simulation results. And this is exactly where the web-based simulation using multidisciplinary optimization engineer role becomes invaluable. Now, just to give you a brief overview of the MDO role, it not only does the simulation automation, but also allows design exploration and optimization to find best design alternatives that meet the product requirements. We have a variety of industry standard algorithms for DOE and parametric optimization, which enables engineers to systematically explore the design space, perform what if scenarios, and also find the critical factors or the design variables that impact the product performance. And also, as you can see on the screen with the advanced visualization tools, users can rapidly merge, post-process, and interactively analyze large data sets, which helps users to evaluate design options faster and with greater clarity. Now, to automate the bike frame simulation workflow using MDO role, a simulation expert will first create a template that exposes only the parameters that the designer is allowed to modify, so which eliminates the risk of errors. It's not that if accidentally a non-expert user changes something, that will either give you the convergence issues or give you a completely different result. So with web-based simulation, the simulation expert is kind of making sure that designer or the user will not accidentally change the parameters or define a value which is kind of out of the range. And once the expert kind of creates the simulation process and develop a web-based template, and once the simulation template is released, a designer will use that template and will run a simulation from a web-based dashboard instead of using a native client. And once the simulation is complete, the user can review the results or review the KPIs directly within the web-based app. So now let's look at how to build a simulation process. So this is the same bike frame that Kevin has used to build his weld as well as the structural scenario. So what I'm going to do is, apart from the parameters that he imported from SolidWorks, I'm going to create two additional parameters. One is for the rider weight and other for the tube thicknesses. So here, as you can see, I have defined a baseline value as well as I have defined what is the range that designer can play with. So this is the range for the rider weight. And once you create this parameter, you just need to assign that parameter to an appropriate feature. So in this case, I'm assigning that parameter to the load input. And similarly, the tube thickness parameter, which I have created here, I'm just assigning to a thickness input in the section definition. So here I'm just assigning the parameter. So creating the parameter is also very easy on the platform, as you can see. And once I assign the parameters, I just want to make sure that the parameters that I assign, the simulation is running just fine. So now the simulation is completed. I'm going to go to my multidisciplinary optimization engineer role, and I will launch the optimization process composer app to automate the simulation process. Now here, as you can see, building a simulation process is fairly easy. All I'm doing is just dragging and dropping the physics simulation adapter onto the process. And that's the only parameter, or that's the only component we need to automate the simulation process. So here I'm just creating a parameter in which it's an object parameter in which I'm going to read my simulation results. So I'm selecting the bike frame simulation. And now I'm going to edit this physics simulation adapter. Here I'm going to define on how many cores I want to run the simulation. And here I'm selecting the single solve mode, meaning that I'm going to run the simulation and save the results in this simulation object parameter. And lastly, I'm selecting upload the images. So all the contour plots such as the von Mises stresses, displacement, or life fatigue life contour plots will be uploaded as a content of this activity. So that's why I'm selecting this upload generated image. The purpose for doing this is because when the simulation expert is going to create the template later on, he can use these contour plots in the simulation template, so that when the user uses this template, he can dynamically see these results when he runs the simulation. And in the inputs, I'm just going to select my design variables. So here, apart from the parameter which we imported from SolidWorks, so I'm going to use one of the parameter, which is the seat tube length. And then I'm going to use tube thickness, and also I have selected the Young's modulus. So let's say if you want to run a simulation for different steel grades, you can make any of the material parameter as the design variable, and you can vary that parameter when you run the simulation template. And lastly, from the scenario, I'm just selecting the rider weight as one of the variable. So we have 4 design inputs. And as for the responses, I'm going to select the von Mises stresses, the log life, and the frame by the weight of the bicycle frame as as the outputs. And lastly, I'm just adding a reference document. So this is just to kind of help the user who is going to use this template down the line to give any supplemental information. Now, in this case, I'm just going to upload an image of the bike frame, which highlights the seat length parameter. So when I create the simulation template, I'll show you the image. And once you set it up, so as I said again, all we need is just the physics simulation adapter to automate the simulation process. Also, setting up the adapter is fairly easy. And once you're done with it, I'm just running the simulation process. Make sure that my simulation runs fine from the optimization process composer app. Now that we have built the process, now the next step for simulation expert is to create a web-based simulation template. So in order to create the web-based simulation template, the expert will go to the dashboard, and from the dashboard, we will launch the Process Experience Studio app. So here I'm just creating an empty dashboard, and I'm dragging and dropping the Process Experience Studio app, which is required to create a simulation template. Now here I'm just creating a new simulation template, and as an input, I'm going to use the simulation process that we have just created. So I'll use the simulation process which we created using Process Composer app. And once we do that, it launches this app where we see all these different components that we can use to create our web-based template. So here I'm just creating a different sections here. So initially I'm just using the simulation process name as the title. So this is just for the methods developer reference, meaning that let's say a designer, when he uses this template, gives any feedback, then methods developer should know which simulation process he has used to create this template. And then I'm going to use again all these different components like input and sliders to define our design variables. So again, the design variables are a seat tube thickness, the seat tube length, and here you can see that for seat tube length, I have defined the range also. So the user cannot change or cannot input the values greater than 550 or less than 500 millimeters. And similarly, I have created the parameters for tube thickness, rider weight, and the Young's modulus of the material. After that, I'm going to use the image that I uploaded in the simulation process as a content. So as you can see, this is the bike design, this is the bike frame, and it shows what is the seat tube length parameter is. And after that, for the responses, I'm going to use our KPIs, which is nothing but one measure stresses, the log life, and the bike frame weight. Now, one thing to note here is that I have set the read-only parameter to true, meaning that the designer or the non-expert user, when he uses this template, he will not accidentally put any values here. Since these are read-only parameters, it will only get updated when the simulation process is completed. So user will not have access to these parameters. The only parameters the user can vary is all the 4 parameters that we have defined in the design input section. So I'm selecting all the responses, and then I'm also uploading the simulation object parameter. This simulation object parameter is nothing but our simulation. Once you run the template, this object will get updated and the user can dynamically view the results in the physics simulation review app. So here, as you can see, I have also uploaded the static images of the different contour plots. And once the developer is kind of happy with the look and feel of the template, he can go ahead and release this template. So I'm just changing the PLM status of this template. And as you can see, once the template is released, the template is now available only as a read-only option. So even the developer cannot make any changes in this template. Now, once the template is released, now I'm wearing a hat of a designer or a user who is going to use this template. So to do that, let me just go to the dashboard where I have created this empty dashboard. And I have these 2 apps, performance study app. So I just drag and drop this performance study app on this dashboard. And similarly, I have the physics simulation review app. Now, in order to run the template, all the designer will do is just look for the template that the developer has released. So I'm just searching for the template. This is the template. And the user will simply drag and drop this template on the performance study app. So now the template is getting instantiated. And once the template is launched, we can see the template that the developer has created. And we can also see, okay, what are the design inputs and the responses. So here you can see that the template is instantiated successfully. So as you can see, I can just maximize this bike frame image. This is the seat tube length parameter. And you can either input the values or you can use these sliders. So let's say I want to run a simulation for seat tube length of 550 millimeters. Now let's say a designer accidentally inputs a thickness value larger than the range. Let's say I put a 6 millimeter. Immediately the template throws an error. It says that please correct the errors. And if I click on this error, it says that please ensure that the value is between 1 millimeters to 4 millimeters. So this kind of guides designer and make sure that he or she does not make any unwanted mistakes. So here I'm inputting the tube thickness as 3 millimeters. I'll just use rider weight as 120 millimeters. And here I have the drop down, and so that I can use a different steel grade with appropriate modulus. So once you do that, we just wait for saving the changes. And once all the changes are saved, the user will simply hit run. So in the interest of time, I'll show you what happens when you hit run. So let me go back to the presentation and okay, so here I just created the template, or I just instantiated the template. And now when we hit run, SolidWorks get launched automatically in the background. It updates the CAD as per the design inputs. It saves the model on the 3D Experience platform. Along with that, it changes all the design inputs that we have defined, that is the tube thickness and rider weight and the Young's modulus. It will run all the entire simulation. And as you can see, since the simulation is running right now, the maximum one measure stress is 134 MPa. And once the simulation is complete, you can see that all these KPIs have been updated. Now for the new design inputs, the maximum one measure stress is close to 190 MPa. And it also updates all the contour plots. So now we can see the static images of this contour plot in the simulation template. So now you can get a sense that even though a designer or a user is not familiarized with the process, or even he doesn't know how to set up the weld fatigue, or how to create a mesh or create a scenario, within a few clicks, he or she can run this advanced simulation with just few clicks and analyze the KPIs. And once the simulation is complete, let me just go back to the dashboard again. You can, as I mentioned earlier, you can view the static images of the contour plot, or the user can just drag and drop this simulation object in the physics simulation review app. So the simulation is now getting loaded. So this is a lightweight visualization where we can quickly view the results in 3D. So this is the log life contour plot. We can see the mean and max. What is the lowest fatigue life? We can just zoom in and see where the fatigue hotspot is. Also, you can view the model information also. So if I uh, go back at the home, you can see, okay, what is the mesh quality? Okay, what material we have used for this analysis? Again, for the structural analysis case, I can see what was the scenario setup, okay, how I have applied the load for different load cases. And also I can see the displacement and the one measure stresses. And you can also play the animation. So you can quickly post-process the results in this lightweight visualization once you run the simulation from a web-based dashboard. Again, we did not open the native or the rich client to run any of the simulation. I just open the dashboard in Chrome or a web browser, and I'm just running this simulation from a web. And also, if you want to do further post-processing, you can always open this simulation object in the Physics Results Explorer app in the native client. Now, so that's about post-processing. Now, let's say if we want to optimize the design, or if we, let's say, want to explore the design space, even that workflow can be automated using the same process. Meaning that the simulation expert will build the simulation template and release the web-based simulation template. And after that, a user will use that template to run the simulation from a web-based dashboard. So let me show you the process for how to kind of automate or democratize the DOE study. So here, this is the simulation process that we created earlier. Now all we are doing is we are just dragging and dropping the DOE adapter onto the simulation process. All right. So here I'm just dragging and dropping the DOE adapter onto the simulation process that we created earlier. And now once we select the appropriate DOE technique, I'm just parameterizing the inputs that we can change in the simulation template. So number of inputs is one parameter that I just created or I just mapped to a parameter. And then in the factors, the design range or the parameter range is something I'm going to parameterize. So when we create the simulation template, the designer can or the user can change this design range to run a DOE study. And for the DOE responses, I'm going to minimize the mass and maximize the fatigue life. That's going to be my objective. And since we are running multiple design points, I'm just going to make sure that I use this low disk usage option. And with that, once this DOE process is ready, I'm just going to create a simulation template. Now the simulation template is going to be similar, just like what we did earlier. I'm going to use all these inputs and slider components to create the upper and lower ranges of these parameters, so that when the simulation or when the user is going to instantiate this template, he can just define the range and the number of design points as input to run the DOE study. So again, when the methodology developer releases the template, the user is going to drag and drop this template in the performance study app, and the inputs are going to be the range of the parameters and the design points. So here I'm just using 20 design points to run a DOE study, and that's pretty much it. You just hit run. The DOE study will run in the background. Uh, the process will automatically update the CAD as well as all the design inputs, run the simulation as well as the fatigue simulation, and will give the KPIs. So once the simulation is complete, in the monitor tab, you can quickly analyze the design points. It will tell you how many design points have passed and how many design points have failed. And also you can quickly plot like a 2D scatter plot to analyze the effect of design parameters on the responses. So this is like the very crude post-processing you can do in the monitor tab. But to do advanced post-processing, what we are going to do is we are going to use this results analytics app. So I'm just dragging and dropping the results analytics tab on the dashboard, and I'm dragging the simulation process in the analytics tab. And now in the guided analytics, what we are going to do is we have the steps defined for the guided analytics. As you can see at the bottom of the screen, the first step is the preview, where we can see what is the DOE setup, all the inputs, outputs, and even the parameter statistics. It really shows, okay, how many parameters or how many design points have passed and failed, and also the statistical distribution for each of the design parameter. That is what is the mean for each parameter, as well as uh, the distribution or what range we have used for that particular parameter. After that, we go to the define and oops, sorry. After that, we go to the define step where we see that, okay, where we can change the priority. Now, if you remember in the optimization process composer, we selected that we want to minimize the mass and maximize the life. And that's why it has the priority of must have. But you can also change the priorities. And changing the priorities will dynamically change the scoring and ranking of the designs. Here you can see that we can filter this large data set by using the different filtering parameters. You can filter the data based on the parameter ranges, or also based on the scores or the feasibility. So here I'm just showing the top 5% of the designs. And now here on the screen, you can see that the design points highlighted in green are the Pareto points, which are the most optimal design points. The ones highlighted in white are the feasible design points that satisfy all the constraints. If we have any infeasible design points, then they will be highlighted in red. And all the gray ones are the excluded design points, or the points for which the simulation has failed to run. So here I'm just filtering the data based on the different parameter ranges. And after that, you can add the designs to basket to compare for the later stage. So here I'm just adding multiple design points as a favorite. And once I do that, I go to the compare step where I can compare the alternative side by side. Again, I can change the static images of the contour plot. And also I can use something called as the objective comparison. Now here, as you can see on the screen, the outermost points better meets the objective, meaning that in this case, the design alternative 18 has the maximum fatigue life, but it also has the maximum mass. Whereas design point 20 has the minimum mass, but it also has the minimum life. And therefore, I'm just selecting the design point 9, which is somewhat in between the design point 18 and 20. You can also see these results. I mean, if you click on the table format, you can see the results in the table format also. And as you can see, the design alternative 9 is somewhat in between 18 and 20. And lastly, you can go to the collaborate tab, where again, here you can change the parameter weightage, and it will dynamically alter the rank and the score of the different designs. And based on that, after you study the designs, you can study which is the recommended design. So I'm just selecting the recommended design here. And lastly, I'm going in the recommend tab where I can define or I can add my comments. And you can share this tab or share this dashboard with the other designers. And now the other designer can change the parameter weightage based on his or her requirements and find out which design meets which design best meets their goal. So here you can just share the dashboard or the tab with other users, or you can share this with your managers for review. So in summary, as we can see that by combining the power of SolidWorks and 3D Experience platform, we can democratize the simulation and really empower the non-expert simulation user to do these kind of advanced simulations early in the design phase and explore the design space that can help them to optimize their designs very efficiently. Thank you all for joining this webinar. I hope you found it useful. And if you have any questions, please feel free to reach out to us and we will be more than happy to assist you.